Okay, so now I'm going to talk a little bit about the observations that we use in synoptic observations, meaning that we have quite a good accumulation of time series of certain observations where you can look them up, where you can request them, in a sense. So with the caveat that here I'm talking mostly about space missions, and because these are very adapt to do synoptic observations, however, not in too much diverse emissions, but let's say in the emissions that we need them to be, basically mostly UV. Although we still need other spectroscopic information from ground, but for example, ground space observatories are more equipped to observe a certain area of the sun for a long time with a very high resolution, spatial and temporal resolution, basically, to study spatial. Although this is also applicable for space weather, because studying spatial cases is basically how we derive certain physical understanding about the phenomena. Okay, so yesterday Eduardo mentioned Solar Monitor. So this is a very nice website. It's like observer's best friend. Even if you're on ground observation, you first basically go and check Solar Monitor. So this big no data, unfortunately, from ground-based observations, because of course, if the weather is bad, it's bad. What can you do? But it's very important H alpha line, which is basically where you can see prominences and brightness, flare brightenings, and so on. So quite important as well. And then you have the magnetosphere information from SDO. You have white light continuum, basically when you see the sunspots, and then coronal imaging and also X-ray coronal imaging, which is sorry, like really high in the atmosphere. And you have a little nice catalog here with the classification of the active region according to Hale and Macintosh. You have sunspot area, which is also quite important for example, if you study flares, if you study solar irradiance as well, and number of sunspots in a. So basically, we have an active region. It can make more than one sunspot developing inside of it. Okay, so then you can go and just look at the magnetograms closer up, because you want to see certain configuration and want to select an active region like this. So basically you click, all this is clicking, right? You don't have to do anything, just click on the active region, it appears. With the coordinates, which is also very, very nice to have when you observe and you have to catalog your information about your observations, or if you have for example, you're doing forecasting and then for active regions, and then you want to check is your forecast for this region was correct. You can immediately go to Solar Monitor and check what's happening. And if this is the correct active region in your data set, where you expect it to be. And here it's not really visible, but you can go into more details with, like, it's under the what the coding is, but you can go into more wavelengths to just inspect this particular active region in different wavelengths, and then you can actually go back and forth in time, depending, like if you have forth in time, to see how the region evolves. Like, so this is a very nice, easy, quick view way to trace your observation. Another such tool is the Solar Helioviewer, which basically combines many instruments. So here you can, on this side, sorry. Right, on this side, you can select different instruments. It's very fun. You can overlay them, basically creating a composite information. You can overlay, for example, HMI magnetograms with the coronal loops and see how, where the polarity distribution and actually where the loops appear in correspondence to what's happening in the photosphere. You can also, here it's not SDO, you can use SOHO. I think you can use historical observations with Yoko and some other instruments, IRIS, I think as well. Not all these instruments are full disk. Some of them are just observing a very specific bright region as well, but probably this is what you're focused on anyway. And then here you have quite a lot of information, all types of features from NASA, from ESA, from not independent, but other classification schemes that you can basically bring forth the numbers, the classes, everything that you may need. And here it's even some SPOCA, which I think identifies active region coronal holes as well, which coronal holes are important for solar wind properties when you want to model the solar wind parameters between sun and earth, and then if you have a CME, also model those parameters. So it's quite nice overview. You can rotate it. You cannot really rotate it, but you can play it forward or backwards, and zoom in, zoom out, and make nice here on the top. You can make images and videos, basically, and embedding. So if you need for presentation, paper, all fun. And something that I find extremely nice is also, I hate transferring coordinate systems. So it gives you here several options to do coordinates of active regions. If you're studying some time series of an active region, for example, you can use several different types of heliographic coordinates. Right. So, and as I said before, space-based is nice, but there are also very crucial information coming from ground-based observation, particularly the H-alpha. I think there is only one satellite which measure H-alpha, and it's a Chinese satellite, and I'm not even sure if we have access to that data or if it's still flying. So basically, this is the Gong network, and it's mostly known for its H-alpha, for in space weather, for its H-alpha observation. So you have these different instruments more or less spread out around the world. So you have Hawaii, you have Canary Islands, you have Big Bear here, and other places. So this is a way to monitor chromospheric activity as well. So I'm not sure if you see here well. So you have hot active regions, you have prominences also at the limb, and you have you see very clearly large filaments, which the large filaments are something that their position and their polarities is something that is related to the solar cycle and the flux transport. So this is important information. And the other thing that Conch is very famous for is helioseismology, which can have implementation also in space weather. So when we study flare active region evolution, in a context of flaring activity, we can use helioseismology to detect or like predict the emergence of flux or certain instability coming, which are related to flux accumulation and instability development for flares. And of course, there is SDO, which is the core instruments for many, many things. We really don't have anything that is as wide in observation as SDO. It's not the only instrument that observe like this, but it has quite a high resolution in several wavelengths, and it's also have data products like velocity field, magnetograms, as I said. So this is basically a mosaic, telling you in how many ways you can see the sun here. And it's also there is a set of parameters, sharp parameters, which are particularly developed for space weather studies. So these are a time series of active regions in different, so these are cutouts of active regions, right? So, and in different, with different images, like, as I said, continuum Dopplergrams and magnetograms and vector magnetograms, which are very nice because you can actually see the components of the vector magnetic field and use that to do predictions of flares in CMEs. And it also provides a measured set of measured inferred magnetic field parameters and current parameters and information about size and helicity, basically rotation in the active region and so on and so forth. So this is something that is widely used for predictions. And it's all based on SDO. And if you don't have SDO, it gets complicated. So the AIA has it has 10 wavelength channels. So these are broadband observations. So it's not in a certain part of the line, but you have a transmission profile where you basically gather the light in this wavelength range. And also these wavelength ranges are, I think I mentioned, related to certain temperature. Mostly we care about the plasma density and temperature properties in the different spectral wavelengths. Okay, this is right. This is an overview of the SDO observations. So there is one more that we don't use that often, which not everybody are aware. There's EV. Basically, it stands for Extreme Ultraviolet Variability Experiment. So it measures the total solar irradiance in certain wavelengths, which is something that we should be aware when we study the impact of enhanced emissions on the terrestrial atmosphere. So it has basically everything that you need, which is very nice. And yes, as I said, here you have these three here may appear similar, but they are basically the different components of the magnetic field, radio, and then colloidal and southward. Right. Okay. Right. So this is the previous, I would say, instrument to SDO. In a sense, it has like a large experimental setup. It has a little bit more observational capacity. It's reached 30 years basically last December. So go back for a moment. So it has a remote sensing, meaning imaging. And maybe one of the most famous one is the LASCO chronograph, where you can see coronal mass ejections and the streamers. To study, you have the UV imaging, which is at this time, most people use SDO because also the resolution is better, but it's also a very good source of observations. And the MDI, which is basically the photospheric magnetic field inferred for 30 years, which includes, in the beginning, I show you this 2.5 cycles, which is tons of information that we need to understand and properly model the solar dynamo. So these are the most famous, most used one, but also comes with some spectroscopy instruments, basically measuring some absorption and emission in different wavelengths. And also it has in situ measurement of the solar wind and solar energetic particles. But there are newer missions that are like more famous for this. But the nice thing when you have a suite like this is that you can basically use them simultaneously, and then you can trace from the coronal loops out to in the interstellar space what is happening, and having also information in white light and magnetograms. And this is for 30 years. So this is absolutely extremely important data set and unique in that sense. So the solar orbiter is the new thing. Maybe the most famous objective of the solar orbiter is actually going to see the solar poles and how the magnetic field there is distributed, because when we, again, this is a question of the cycle of flux transportation, which is related to the activity, a system of systems, as I said before. So we have very little information how things appear at the poles. It's a special place. Also, the differential rotation between the equator and the pole is different. And sometimes we have a switch, basically, of velocities between the equator and the poles, which is like an interesting phenomena, and this affects apparently the flux transportation and how the next cycle will be built out of everything that's happening in the current cycle. So, of course, there are other things important for solar orbiter. So it's linking again in situ measurements of different media to the source on the sun. It also allows us to trace the CME shocks and solar wind propagation and help us connect. So figure out the connection between that and how it's actually physically, magnetically connects to the planet's magnetospheres. Again, if they have one. So it has remote sensing and in situ data observation. So these are many, many instruments, and they are created in different institutions around Europe and US. So, for example, I know about the, because it was built where I was doing my PhD, the X-ray spectrometer telescope, basically observing the solar output in X-ray, like high energetic particles. And then you have magnetometers and imaging and solar wind in situ measurement. So it's quite a lot. So one thing, so these are just images, information for electron density and magnetic field from the different orbits. So the good thing is that it's very high resolution, and it's almost continuous when it observes. So this is basically what you need. And here, as I said, the nice things about the poles, these are something that we have not seen before. And you see here, for example, things get complicated to understand, also because the projection effect uh, at the limb area. But this is probably the clearest visual that we have ever had so far of the solar poles. This is another schematics, basically, of current scientific work going on with solar orbiter, and again, how we basically can trace the connectivity between the solar magnetic field and the rest of the heliosphere, and we can measure in situ from just background wind, from CME, and so on and so forth. The thing, so if you want, sorry, this data set, there is actually, it's probably a good time to say this, in ESTEC, I think, where was Panos, do you remember? So the deadline is basically, it's a free school kind of situation. The deadline is in the end of June, yeah, where you just have to apply, and they, in this ESA center, I forgot where was ESTEC. ESTEC, yes, in the Netherlands, where you can get a lot of information of how to work with data of the data set, how to acquire it, and how to like do copy for certain experiments with the data set. So it's a nice thing that I should have probably put the advertisement, but I just remembered it. They are starting to talk more about the community use of this data set, so they're trying to spread the word.